So good morning, good afternoon, good night, or good evening. It's a pleasure to have all you today to attend the last talk of this 2020 season of IEEE Circuits and Systems Society Rio Grande do Sul talks. So for us today here is an honor to have Professor Rabaey from UC Berkeley and IMEC Belgium. But before doing his introduction, I'd like to do some few announcements of next events. So next week we have CERESA, the 16th International School on Effects of Radiation on Embedded System for Space Applications. So the registration is free for all IEEE Circuits and System Society members. You can see that after going around the world in several continents, so this year is a virtual edition from Porto Alegre. You can address the web page to see the full program and also to do your registration. Also, the week after, we have the Seasonal School on Electronic Design Automation from December 7 to 11. Also, free registration to all IEEE CASS members. So this edition is a special one where all the slides will be in English, but the audio will be in Portuguese. You can also address the web page to see the full program with speakers from academia and from industry. Several ones work in the major EDA industry. I'm sure that you are going to like the nice program that was set. Also, I would like to encourage all of you to participate to the IEEE Circuits and Systems Society Student Design Competition that has 3 phases. You can go to the web page to see more details. There is very, very nice awards for the winners teams in each region. And also the final competition will be at ISCAS in South Korea in May 2021, hope face-to-face, and registrations are open till next December 15. Also, 16, 17 December, we have the final meeting of our Rio Grande do Sul chapter of CASS with a very nice program that will be announced soon. You can also go to the YouTube page of the IEEE Circuits and Systems Society Rio Grande do Sul chapter to see a significant set of recorded talks from the CASS talks that we have done on Fridays, and also the industrial talks that were done each Wednesday. Also, next year we have, as traditionally, last week of April, the Microelectronics, South Microelectronics School and the South Symposium Microelectronics. So soon you are going to have more details about. And also put it on agenda next year, last week of July, the first seasonal school on monolithic 3D. And it's also agreed that the following editions will be in France, Singapore, and China. So today here we are to see this very nice talk of Professor Rabaey that always do very nice talks. So the title is Of Brains and Computers. And Jan is a professor in the graduate school in the Electrical and Computer Science Department at the University of California at Berkeley, where he held of the Donald Pedersen Distinguished Professorship for 30 years before retiring. Before joining the faculty at UC Berkeley, he was a research manager at IMEC from 85 to 87. He is a founding director of the Berkeley Wireless Research Center and the Berkeley Ubiquitous Swarm Lab, and has served as Electrical Engineering Division Chair at Berkeley twice. In 2019, he also became the CTO of the System Technology and Code Optimization Division of IMEC Belgium. Professor Rabaey has made a high-impact contribution to a number of fields, including advanced wireless systems, low-power integrated circuit, mobile device, sensor networks, and ubiquitous computing. His current focus is of the interaction between the cyber and the biological world, amongst many other things. He is the recipient of major awards, amongst which the IEEE Max van Valkenburg Award, the European Design Automation Association Lifetime Achievement Award, the Semiconductor Industry Association University Research Award, and the SRC Aristotle Award. He is an IEEE Fellow, a member of the Royal Flemish Academy of Science and Arts of Belgium, and has received a number of honorary doctorates. He has been involved in a broad variety of startup ventures. So this is just a short CV, because if you decided to read the full CV with the full achievements of Jan, we would take several hours to tell you about. So thank you very much, Jan, to accept our invitation to do this talk today. But I also would like to invite all the attendees also to consider to do a subscription of our IEEE Circuits and Systems Society YouTube channel, if you have not yet done. So there is now more than 1,200 subscriptions. So now it's time to give the floor to Professor Jan Rabaey. It's a pity that this time you are not here in the south of Brazil to walk a little bit near Itaimbezinho, as we have done another time. But thank you very much to accept this invitation, and the floor now is with you.
Thank you, Ricardo. Good morning from Napa Valley, California. Pleasure meeting you all, wherever you are in the world and what time zone you're in. So the talk I'm going to do today actually is called, as you see, of brains and computers, and is a talk which is a little bit more philosophical than I typically tend to do. It's kind of some musings about how computers and brains are related and how they might have a joint future. So without further ado, let's look a little bit at how computers have evolved. Computers, as we know it, basically started to arise around 200 years ago with mechanical computers, and then went to vacuum tube, mainframes, mini computers, PCs, laptops, smartphones, wearables. So what you notice is they have gotten smaller and smaller over time. So that's one important type of trajectory. The other one is very important as well, is that at the same time, around the 1970s, the internet, basically the DARPANET, got created, and that enabled another revolution to happen, actually, where computers are not single entities, but are actually networks of elements connected together. We obviously all know the World Wide Web, and we have these massive compute centers and cloud computing, and now we're starting to talk about swarms, a huge number of small devices connecting together. So if you look at the trends that we then observe, is that computers have gotten smaller and smaller and smaller. If you think again over the last 60 years or so, where we go from volumes of 10 to the 12 cubic millimeters, nowadays with we have basically smart sensors that are out the scale of about a cubic millimeter approximately. Now, obviously, a lot of this has been driven by the compute elements that are behind it, or transistors, which have gotten smaller and smaller as well. Today, we're talking about, if you look at the most advanced products out there, are basically in the 5 to 7 nanometer node. And it is foreseeable that about 5 to 10 years will basically be around 2 to 1 nanometer type of devices. So driven by smaller transistors. Now let's look at the other part of the compute world. The computer we all carry with us, our brain, that has also been evolving actually for a very long period of time. We can go back almost to the origin of the Earth, about 3.4 billion years ago, when the first bacteria started. You observe that over time, systems have gotten more complicated. First, they started seeing some communication or some actuation using electrical signals. We had the first neurons that arrived. We had the first networks of neurons that basically help to drive more complex entities with more complex functionality. But ultimately, about the brain itself has started to merge around a couple 100 million years ago. Now, humans, basically, the modern humans appeared about 200,000 years ago, and about 80,000 years ago, we finally had cognition basically started to arise. So brain evolution, again, an evolving thing, but has happened over a very long period of time. Now, similar to our computer world, brains typically are standalone entities, but using a set of senses. speech, vision, and things like that, we manage to communicate. We actually, a lot of humanity basically works because of the fact that we have groups of people working together, communicating with each other, interacting with each other. Now, if you look at the human brain evolution, you see just the opposite of what we observed from our computers. You see that millions of years ago, the brain was very tiny. If you look at the original type of humanoids, we're talking about less than 500 cc. While today, if you look at Homo sapiens sapiens, the brain has gone up to about 2 liters approximately. So a lot of the improvement in compute capabilities have become because of an increase in the volume of the computer, just the opposite than what we've seen for the electronic computer. Now, if you start looking at putting both of those compute paradigms next to each other, we see that there's some very important differences. If you think about computers as we know them, we built computers to perform certain functions. We built them to execute algorithms. And the optimization you're trying to do is to basically make sure they do the algorithm well, but at the maximum performance while minimizing energy and cost. That's really the design principle of the computers as we know today. The brain mission is completely different. The brain has been structured to basically for the following function. It is basically to help basically the owner of the brain to survive, to prosper, and actually procreate, basically make sure that the species basically is successful and extends out. Now, rather than basically trying to maximize performance, the key function of the brain is to maximize reward. Reward at a minimum energy cost, because energy, as we will see, is one of the driving behaviors or the entities, the driving goals behind the whole evolution of the brain. Now, the way the brain does that is not through a set of instructions, as we see in our basically a traditional computer. The brain basically performs as a set of loops. There's 2 loops actually that are kind of dominant. First of all is what we call the metabolism or physiology loop, which basically makes sure that we survive. It basically observes how our system, our body is behaving. It collects from a variety of sensing elements information, which are called patterns, and gradually it combines all those things together to get a big picture. So it examines a large pattern, which it then compares to what it knows, and as a result of that, creates action. Action that makes, for instance, our heartbeat, basically make us basically eat, all those type of things. Now, at the same time, there's a second loop that basically interacts with the world around us, observing what's happening with us. So that's your various senses, which is basically, obviously, your vision, your auditory, your smell, your taste, your touch. Again, we observe patterns, we combine them into larger patterns and compare them, and we perform actions as a result. So we have an inner loop and an outer loop type of behavior. But the key thing is we operate on patterns, not on instructions. Now, the approaches to basically be successful to their task are very different. As we already said, the way our current computers work is they are based on instruction set computing, the Turing machine and the von Neumann type of concept. You execute sequentially or in parallel a set of instructions. The brain, on the other hand, works on patterns, as we already said. It observes patterns, it interprets patterns, and it acts on patterns. So it is very different. It's also, while the computer, the electronic computer, as I said, is based on instructions, the biological computer, the brain, is basically based on learning. It observes the data, it observes the patterns, and basically it augments on that and learns from that. Now, just to point out some more differences, the approaches, again, are between the two are very different. If you look at the brain, sorry for that. It seemed like I got a PowerPoint crash, which hasn't happened in a while. See if I can get back to the presentation quickly. 1 second. It didn't like that little movie, I assume. Okay. Okay. So what you see here is a cross-section of basically the simulation or animation of the activity in the brain. What you observe is that it's very data-driven. It's event-driven. It's very sparse. Most of the brain typically doesn't do very much, but then when you have the right activation, things happen. So event-driven type of activity is the key operational paradigm of how our biological computer works. If you look on the other hand on how we build our most complex computers today, they're all driven basically by a very rigid timing regime, where we basically use a central clock, which we then distribute and synchronize the various elements and basically dictate when action will happen. So again, very different perspectives between the two. Now, just to kind of summarize a little bit what we've seen so far, if you look at the brain, a couple of key properties that we should be aware of. Basically, it's learning-based. Most of the computation is done in a statistical base and is mostly analog. You might argue it's discrete, but anyhow, it's basically statistical. It's a law of numbers, basically. It is very robust because it's overcomplete and redundant. As I already said, it performs computation not on numbers. It doesn't have floating point. It doesn't have anything like that. It performs computation on patterns using things like phase relations and distributions. And randomness is a key feature. And we'll talk about some of the other properties later on. Basically, function, there's no time multiplexing happening in our brain. Function is mapped to space. Memory and logic are very closely intertwined. Again, in contrast to the von Neumann machine, where they're basically very separate entities. Here they're intertwined. The brain is embarrassingly parallel, and as I already said, computation is sparse. All right. Now, the challenge we see is that both approaches, both the physical computing and the organic computing, seem to be at their limits. We all know that technology scaling is somewhat slowing down. We still will go to smaller nodes, but the advantages in performance and energy consumption are basically diminishing. Again, Moore's law will continue, but it will primarily be to the number of devices we're going to be integrating. So getting more computational power, computational capability is getting harder. The same thing is true with the brain. How would you make a smarter brain? There's a couple of options you could have, right? I could increase the brain size further, as we have done in the past. Or you can have denser interconnect between the neurons. You can be faster, like increased signaling speed. Or I can make my neurons smaller, so that I can pack more neurons in the same domain. Now, all of those are possibilities, but come with penalties. Because if I might make my brain bigger, you have to communicate over longer distances. It's going to slow down, and it's going to take more energy. If you make the neurons too small, they become noisy, very noisy, and at some point in time, it's going to be very hard to have some meaningful computation. So it's that trade-off between more intelligence while at the same time dealing with noise, energy consumption, and basically computational speed. And actually, to talk about energy, both domains, energy is the limiting factor. There's an interesting chart that shows how the amount of glucose you have to basically ingest in per minute, basically, to make your brain operate is proportional to the size of the brain. So you can see the more neurons I have, the more glucose I have to take, the more I have to eat, the more energy I have to provide. At some point in time, you do nothing else than basically consuming energy or basically getting food in. The same thing is true with our electronic world, where the size of a device and how much compute power I can put in it is actually limited by the battery size it can fit the amount of energy I can fit within the volume of the device. So again, key challenge is really dealing with energy and power. That's really what we need to think about going forward. Now, there's some other limitations that come with this. So the brain, if you think about it, the amount of energy I can consume is very constrained. To be operational, our brain can only go between 36 and 37 degrees Celsius. If it gets out of that range, it doesn't work very well. Also, the amount of heat I basically can, amount of energy, the amount of computation I can perform depends really on how fast I can remove the heat. And the heat, as you know, in the brain is basically removed by the arterial system, is basically your blood is cooling down and takes the heat out. And the kind of the heat removal rate is about 15 milliwatt per cubic centimeter. So you can imagine if you make a bigger brain, obviously I have to improve and increase the amount of heat that I can remove. Now, we have the same thing in electronics. Things are a little bit simpler there in the sense that we can operate over a much broader temperature range from minus 45 to 85 degrees Celsius. And we can remove a lot more heat to about 100 watt per square centimeter approximately. But still, heat removal is going to be a limiting factor, and is a limiting factor how much compute I can pack in a particular volume. So this is in both domains, the biological world evolution, as well as the electronic heat and energy are the limiting factors that we need to overcome. So where does this lead us? Well, I think there's a beautiful opportunity, and I think a lot of us are capturing already, is to cross-contaminate between the two worlds. Can both worlds learn from each other, get the best parts of each other to basically make both biological and physical computing, or the merger of the two, move forward? So convergence. If you look at it, in one sense, we already see some robots that basically are starting to get some humanoid intelligence by basically putting artificial intelligence, by putting a variety of sensing patterns, information about the world around us. We're starting to actually build copies of the human being in basically physical structures like robots. Similarly, we're starting to augment humans by basically adding extra senses, basically by having AR, VR, by having extra hearing aids, hearing enhancement, by augmenting the sensing capabilities. We basically start getting more power into the human brain. So we already see some of that convergence happening. Biological worlds become more physical, and the physical world become more biological. Now, the interesting part is that the crossroads actually shows that actually we are basically starting to get at a point where both systems start to become similar in complexity. If you think about the brain consists of about 80 billion neurons, as I said, in a volume of about 1 to 2 liters. Neurons are about 4 to 100 micron in size. We have about 100 trillion interconnection points, 20 watt power average, and it's estimated that the brain performs at about 10,000 teraflops. Again, you can argue about that, but this is the computational capability. Now, we think about where we are with CMOS today. Actually, the most complex chips are starting to basically put about tens of billions of transistors on a single die, which means that they become similar to the complexity of a neural network, even though neurons obviously are more complex than transistors. But that trend will definitely go forward. The volume is smaller, but still chips can be about 400 square millimeters. Power dissipation is between 5 to 150 watts for computing type things, so substantially higher still, because the amount of computation we're really getting is about 10 teraops or teraflops, 100 teraflops. So computational complexity is still not there yet. But you can imagine that going forward, both systems will become similar in complexity, and maybe electronics will surpass what biology can do today. The other thing that we see already happening is that, as I showed you before, the computational paradigms between the two were very different. But actually, again, we see convergence. A couple of things are happening in the compute world. that basically make them more and more resemble what a brain looks like. So we're moving from the traditional processing domain, where you had a data pod that basically talks to memory, fetches instruction, thing like that, very instruction oriented, very sequential. We basically, over the last decade or so, we've seen many cores, multi-cores, and all this type of thing, where actually the memory, sorry for that, start moving into more and more closer to the processor and even inside the processor. So we are starting to see systems where memory and logic get interwoven with each other, where processors are basically only turned on when there's data. So the whole event-driven capability starts to, or basically model of the brain starts to actually to appear in our physical compute devices as well. And you also see that learning is becoming a very important factor. So rather than programming these devices, we are starting to basically use data to program them effectively. So there's definitely some convergence happening between two domains: in-memory computing, learning-based computing, and event-driven computing. Three factors that were biological are now appearing in the physical world. Now what I'm going to do is the rest of this presentation, I'll basically look at some of the design principles of the brain and see how well they could apply to our next generation physical computers. So lessons from the brain. Now, before I go there, I have to put some caveats, right? This is from a quote from my colleague and friend, Bruno Alshausen, who's a computational neuroscientist, who stated the following: the biology is hiding its secrets very well. We just don't have the tools to grasp the complexity of what's going on in the brain. Now, that is true. At the same time, we're developing a lot of tools that actually help us to get some insights in what the brain is doing. So progress has been swift. And I think more and more we start understanding what the biology is doing. And again, this could help us to get some insights on how to basically build more effective computers. Actually, there's a beautiful book written by Peter Sterling and Simon Laughlin that talks about principle of neural design, which is a very interesting book in the sense that it takes engineering concepts. It tries to take an engineering perspective on how the brain operates and what the key design principles are in basically how the brain operates. So I'm basically going to walk you to some of those principles because I think they're very illustrative and very interesting to observe. So here's principle number one, which is a kind of bizarre one. At first shock, it says computed chemistry whenever possible. Now, let me explain that a little bit. If you look at how the brain works, the brain is basically an electrochemical system, right? The way the signals are represented, it goes in the electrical domain. Sometimes it's represented as chemical signals. It goes back and forth. Now, turns out that if you want to be extremely energy efficient, actually chemistry turns out to be a lot more effective than basically using electrical signals. Just to give you an example here, this is a picture of a cell. This is the cell boundary, the lipid bilayer. And for the cell to communicate with the outside world, it has to open channels into the cell boundary, into bilayer. And that's done by using proteins that are arriving, they're docking, they're basically creating some chemical reaction that opens the channel. Now, it turns out that if you look at that protein style computation, it supports actually virtually everything that we have seen that we have been using in our traditional computational world. It supports analog functionality, it can amplify, it can oscillate, it can integrate, differentiate, log powers, you name it. All of those functions can be implemented by using proteins and basically various complex chemical structures to interact with each other. It also can perform digital operations: add, subtract, multiply, divide, and compare. So very powerful and very energy efficient. To open up a ion channel in the lipid bilayer takes only 75 kT, where K is the Boltzmann constant and T is the temperature. Now remember that the minimum energy per digital operation that we know and can prove of is KTLN2. So this is the closest I've ever seen anything come close to that boundary, which is the Shannon boundary or Landauer boundary. Now, once you open the channel, then you amplify, because once the channel is open, a whole bunch of electrical energy can flow to that channel. Ions are moving through, where we see then the amount of energy that moves through is about orders of magnitude larger. So extremely energy efficient, but it is very slow. Opening up a channel like that then take milliseconds, so some of them basically might be taking days. And it's also very noisy. So in order to have reliability, you need many of those channels to operate in parallel, basically. So if you think about energy efficiency, this is an interesting chart that compares various approaches of computation with respect to each other. On one side of energy, the other one is speed. Actually, the most energy efficient approach is the chemical broadcast, something we do all the time, right? We basically use our blood vessels to basically communicate over the whole size of the body. If a particular part of the brain wants to basically send out a signal, it puts it in the blood, it propagates through the whole system, and any device that is interested can basically be triggered by it and activated by it. So chemical broadcast is a wireless, they call it wireless communication, without having a specific link between the source and the destination, is a very energy efficient approach. Then you have the more the next step is obviously the local operation, like I showed you before, open ion channels. That's chemical local. And then we can go up the chain. Electrical analog is obviously, we've shown that before, that is also more energy efficient. The electrical spiking, and ultimately digital. Now, digital has the disadvantage of being more complex as a basic operator, but it can go really fast. So the performance-wise is, you can see, if you want to go to nanoseconds, we go to digital computation. Now think about this for a second. This broadcast idea is interesting. If, for instance, we can do wireless communication, is broadcast by nature as well. It's something we haven't been used very often in our wireless systems. We typically try to create point-to-point connection, but broadcast is ultimately the most efficient way of basically getting energy efficient computation or communication done between various nodes. Now, the chemical idea is interesting, and again, we're starting to use some of that. If you look at a lot of work that's going on right now in RM, resistive memory, or phase change memory, or the new memory strategies, like all of those are basically kind of based on some chemical changes. Like in RM, you basically create a resistive RAM, you create a channel through a dielectric. Phase change, you basically change the phase, and as a result, the resistivity of the devices. So this has the advantage that once you've done it, programmed this device, it's stuck in a particular state and basically is quite effective. The same thing is true if we realize that if you want to do computation, again, as I just mentioned before, if I basically can afford to operate at very low SNR conditions, if I don't need a lot of accuracy, analog computing is more efficient than digital. The problem with digital is that just to do a single operation, it is complex. However, if I want to get more resolution, if I want to get more accuracy, large SNR, then it turns out that adding bits to digital is very cheap. So the power doesn't go up very much, while at the same time we get much more accuracy. And the same thing, by the way, is true for communication as well. If you look at communication, analog computation, communication is the most effective ways of doing things, but digital allows you to have more precision. So again, the same thing that we observed in the biological world holds here as well, even though we're limited in how much chemical computation we basically can do. But again, if you look at some of the sensing devices that are appearing today, actuation devices, we start more and more seeing chemical interacting or biological interacting directly with electronics. So that was principle number one. Let's talk about principle number two. Send only information that is needed and send it as slowly as possible. This is what our neural system is very good at. It only is going to communicate the information that is needed, not raw data. Raw data takes a lot of information, channel away, a lot of energy, and basically doesn't add anything. And very often we tend to transmit things as fast as possible. Again, from an energy perspective, that's not very useful. Just to show you how this is happening in our neural system, here are the connection, the nerves that connect the nose, the olfactory, the optical, the eye, and the auditory, the ear, to the brain. And you can observe some major differences between the structure of those nerves. Look at the olfactory, consists of a lot of fibers, which are very skinny, very small fibers. As you would expect, small means typically slow, right? Because the resistivity, the capacitance goes up, so the RC delay goes up. So it's a slow connection with a lot of fibers. On the other hand, we go to the auditory system, we see we have fat fibers, really big wires, a lot higher performance, smaller RC, but it comes at a cost. The olfactory system itself is very energy efficient, and actually it doesn't matter there to be really fast, right? If I smell something, a smell doesn't happen instantaneously. It takes milliseconds or seconds to develop. So slow processing, slow communication is okay. In the auditory system, where you basically want to hear signals and even differentiate between auditory signals from your two ears with very precise type of delay and latency, speed matters a lot. And that's why the brain has basically decided, or the organic evolution has decided to use more energy added to basically provide better speed. And the optical system is somewhere in between. It's lots of data, speed matters, but it's not as important as it is in the auditory system. So communication is expensive. And the same thing is true in our world, right? If you think about communicating a number of bits, actually, depending upon the performance you want to get, you're going to get more and more energy per bit, right? So it actually, just to transmit a bit, depending upon obviously the various type of wireless schemes I would use, you can see that the amount of energy can go from 100 fan out of 4 type of digital gate structures to about 10 million. For a single bit on Bluetooth LE is equivalent to about 10 million type of fan out of 4 digital computation. So communication is always expensive, and optimizing it in such a way that we basically don't spend too much on our communication and communicate only what is needed. Just an example here, how this works in the biological world. Again, let's go back to the vision system. The vision, if you look at the eye is a very high, very complex sensing system. We have about 130 million photoreceptors in the retina. Now, the problem with this is that transmitting all that information in raw format to the brain would basically take a huge amount of bandwidth and energy. So what the retina does is say, okay, we're going to take only essential information and extract it from there. So feature extraction happens right away in the retina, and only that information is transmitted over the optical nerve, which has about a bandwidth of about 10 to 100 megabits per second approximately. So first thing you do is take all the data, raw data, and compress it and only transmit the information that is needed. And then we arrive in the cortex, the visual cortex, which is a huge, by the way, it's the biggest part of our brain, is basically our vision system. It's the most complex task we do. What we see is that from that small amount of information we get from the eye, we expand it massively. We recreate it, we replicate it, we basically have a huge amount of different components, basically look at it. But the bottom line is we have massive expansion again. So it shows that here, and this, by the way, is also true for the nose, for our touch systems. We basically try to minimize how much information we have to transmit to over the communication channel, because, as I said, communication is expensive. So send only the information that is needed. Again, here's another example. As I said, I've showed you the retina. This is the example of touch. If you look at the touch system, basically what you try to do is minimize the amount of information. So perfect example of how you actually can replicate it was some work that was done at NUS, where they demonstrated that basically by having a bunch of those sensors, combining it all together into a single signal with a bunch of sparks, actually helps you to reduce the amount of data have to transmit over the nerves over a long distance substantially. And the same thing is happening nowadays in electronic cameras, where rather than basically transmitting all the pixels as we typically have done, we basically are now looking at event-driven cameras. You only transmit pixels that are changing. And as a result of that, you can reduce the amount of communication bandwidth substantially. So send only the information that is needed. And again, send it as slowly as possible. Slower is more energy efficient. Okay, so next. Again, this is a concept that, this is my third principle. To conserve space, time, and energy, new information should be stored at a site where it's processed and from whence it can be recalled. Again, that's something we start to get familiar with. It is the whole idea of in-memory compute. Again, if you look at, at the sensory pathway, and we start, let's say, in this particular case, the eye or the nose. First of all, we go to sensing, which is absolutely redundant. It's a very low SNR type of operation, and we get accuracy by having many sensors. Then we do this feature extraction and reduction. Substantially, we basically explore the sparsity information, then transmit it out to the brain where it's massively expanded, and then ultimately feeds to classification, recognition, synthesis, and you name it and name it. There, if you look at how this operates, and this is exactly happening in the cortex, this is an example of in-memory computing. That rather than moving the data to the computer is next to the data and operates directly, and we only enable the computing when the data changes or when it's triggered. So intertwining of sensing, processing, and memory is now something that we start basically performing, basically is now becoming in vogue in digital computing as well. Again, some examples here, smart sensors that have basically already some processing built into it, or more novel implementation approach, tree integration, where we put sensing, processing, and memory together in very coarse form and very close form factors. Again, this is changing the way we think about structuring our computing. This is changing the way we're going to build our next generation devices. A fourth principle, and now this is a complicated term. It's called complicate. That's what the term that neuroscientists seem to be using. When we look at it in our engineering world, we call it customization. Again, here's the principle from a number of papers from neuroscientists that are written that compare various approaches of implementing functions in the brain. The following statement is made: if one design is simple and the other one is complicated, choose the complicated one. What I mean by that is customize the function for the operator at hand. And we know that already, right? So for the last 20 years, we realized that if you basically have a dedicated implementation of a function, you're way more energy efficient than basically do this on a generalized simple processor. So customization is a key capability function. And again, this is something that we now start seeing in data centers and cell phones, where we start seeing accelerators being built for very specific functions. So dedicated hardware. Again, if you look at the brain has been very good at that. It basically has mapped functions into different regions. And every region itself has been optimized. The interconnect structure and the computational structure has been optimized to the task at hand. And again, similarly, we see the same thing happening in our electronic world, where we look at, let's say, mobile processors. We see that, yes, there's a bunch of core processor in there, and we have the GPUs in there, but more and more we start seeing a whole bunch of dedicated function blocks for particular tasks being added to our SoCs. So our SoCs are becoming complicated devices, as we basically have been mentioning. Now, by optimization, by complicating or customizing, we actually can, as I already mentioned, we can become a lot more energy efficient. And again, this is a very simple example of how nature has dealt with this. One creature that people have studied quite often, it's a simple structure, has about 130 neurons, so it's a fairly small kind of nervous system. So it's easy to basically map it, understand it. Is this little worm which is called C. elegans. It's a it's a transparent kind of worm, about 1 millimeter in length, and it lives in temperate soil conditions. It's in your soil. So people have analyzed this in a lot of detail and basically mapped the position of the various neurons in space, where they are, and also looked at basically what the functions they have performed. Basically, what most of those neurons do is help this creature to move forward. So there's some little things that can move to basically move forward and backward. So the neurons in this particular case are directly connected to that motor function. Now, you might ask, why would the neurons happen to be distributed in this way? Well, interesting study was done that someone basically from an EDA perspective basically tried to figure out, basically fed this into a place and routing program that optimizes the wire length. And it turns out you end up almost precisely with the positions of the neuron. Basically, the CAD tool basically could perfectly predict where the neurons would be placed. So in other words, the brain basically has optimized the placement of its neurons in such a way that the wire length was absolutely reduced and minimized. So the most energy efficient solution was come up by a natural evolution concept rather than basically by a pure design principle. So customization to basically optimize energy consumption. Now, I would like to actually put a little intermezzo here. Again, talk about optimality, right? We basically have a lot of tools we developed over the years to perform design optimization and things like that. Now, one thing we have been looking quite a bit at is interconnect, right? How do you optimize interconnect? Well, in the neural world, interconnect is happening to something which is called the axon. The axon basically is the output structure. So the neuron consists of a number of input signals, which are basically your dendrites, feeding the information. There's a fan out which is huge, per neuron about 100 to 10,000 input channels. The neuron itself integrates those and ultimately feeds it to a nonlinearity, and it fires when we basically go above a certain threshold. And then it sends a digital pulse, a pulse basically over that interconnect wire, which is called the axon, that then connects to the synapses connected to the next neurons. Now, the axons can be quite long. Actually, the length can vary from about 100 micron in the cortex to about 1 meter, for instance, in the sciatic nerve. The sciatic nerve is the nerve that connects your back basically to your toes. It's about the length of about 1 meter approximately. So a very long interconnect. Now, so if you can look, it's very dense interconnect network. It seems quite haphazard, but again, a very dense interconnect with a lot of communication. Now, the problem here is, how do you transmit a signal fast over a channel, which is the axon, right? So this is an electrical link, so it will be dominated by resistance and capacitance value, as we know. It's an RC network, in other words. Now, in digital design, we figured out how to optimize the communication speed to an RC network. It's very simple. What you do, if you want to basically get the optimum speed, you start inserting repeaters at a certain distance that's so in such a way that your overall communication delay is minimized. Well, that's exactly what nature has done as well. Two things happen. Basically, if you look at your axon, it is basically surrounded by a material which is called myelin. Myelin is a dielectric insulating material, which basically avoids interference between various neurons. They all would be transmitted signals all over the place. So insulation is important. It also helps to basically manipulate capacitance as a result as well. Basically, it basically helps you to optimize the performance to a certain degree by having this insulation around it. But the second thing that nature has done is every so many distances, it has introduced what's called the node of Ranvier. The node of Ranvier is basically something that takes a digital, a analog signal and that basically propagates to this wire and basically regenerates it. Actually regenerates actually using electrochemical reactions again. So nature has come up with this idea of repeaters on its own. And as a result of that, wires are substantially faster than when you would not have those repeater nodes or when you would not have the myelin. Now, be aware, however, still that nature is a lot slower than what we can do in electronics. If you basically go copper on silicon, we have about a speed of about 150,000 kilometers per second. Now, the delay over the longest axons can actually be about 10 milliseconds. So you can see there's a huge difference still in performance speed between the two. But it's kind of striking to see that similarity in solution that we have come up with. And actually, we know exactly how many repeaters to place. This is actually from my textbook. It basically shows that there's actually a critical delay between, if an optimal structure, delay between wire signals should be constant, independent of the routing layer, only a function of your technology. Well, again, people have figured that out a long time in biological as well. This is a paper from 1903, which talks about the number of nodes of Ranvier of different stages in the growth of the nerve fibers of a frog. When a frog is very small, it has narrow fibers. The delay, the R becomes larger. So once the frog starts growing, the number of nodes of Ranvier it needs for optimal solution is actually going down. So again, it's very interesting similarities between the two. So I'll add two more before basically concluding, two more principles that I basically would like to add. And this one I call the play the number game, right? Turns out that biological systems tend to be highly variant, low SNR, and basically are not what we would typically call high precision elements. Now, the way nature has dealt with that, dealing with low SNR, variability in time and space, is by using redundancy and diversity. For instance, if we look at our olfactory system, or nose, it consists of millions and millions of sensors. Those sensors are not very good at all. The SNR is, the selectivity of them is fairly limited. And one sensor actually can sense a variety of various molecules. But the way we get precise smell is by using that redundancy, by basically using the fact that we have so many sensors that we start seeing statistical population build up, and that's the way we actually can get very precise smell. And this is true for touch as well and for other senses as well. So an interesting thing, basically, we use statistical behavior to get basically accurate response in the presence of a lot of noise and variability. And the final neural principle that is really crucial, and that's something we haven't been able to build in electronics very well, is, things will degrade, systems will vary, will have statistical variations happening when you fabricate a device. So the way our body deals with it is by continuous calibration. Remember the inner loop I showed you before: self-calibrate, adapt, and heal. Again, here's how we do this. Our body continuously measures a bunch of parameters, that basically metaphysical parameters, and basically uses this to adjust a number of feedback loops so that the temperature of our body is fine, our heart rate is correct, we have enough energy to the various muscles, we have enough food at various places. It actually predicts some of the behavior. It knows when you wake up in the morning, you're going to be hungry, so you start preparing your basically ingestional system, things like that. So very much based on an internal feedback calibration system. Again, this is something that didn't happen at all in the digital computer world, but is starting to happen today, right? Here's another example of how, for instance, we use adaptation to optimize performance in our brain system. If you look at your eye, right, your eye basically, if you look at the retina itself, doesn't have a constant resolution. Actually, the center of the eye has a much higher resolution than the edges of the retina, which is kind of normal, right? So the area of the highest resolution is called the fovea. Now, if I want to look at something, I would like to have the highest possible resolution, right? So that means you have to move your eye in the right direction. You have to basically focus on the domain where you want to look at and have the highest resolution. All of this is basically performed by a closed loop system where you have basically your signal here. The blue, this is your optical nerve coming from your eye. The blue is the information, the optical track, which then ultimately goes to the cortex where we do processing. But actually somewhere, just where the eye comes into the brain, there's something that observes this and looks at light input patterns and actually helps it to drive right away the motor function which orients the eye. Now, that's not the only control. There's more control that comes from the cortex. Basically combines two things together. It combines both the observation, the physical thing that you see where the light is coming from, but also with the high level intent. I want to look at this. That's basically coming from your higher level of the cortex. So this area here basically do exactly this colliculus is exactly combine those two together to basically drive the eyes out. Again, instantaneous adaptation and auto tuning to get the maximum performance. Again, we are starting to do some of that in our digital world. If you look at some of the most advanced mixed signal systems, where you have sense and transducers, actually it makes sense to keep the signaling path as analog as possible, right? Because it's cheaper, it's energy efficient to do something in the analog domain rather than doing conversion right away in the digital domain. However, anything that's done in the analog space is might have issues with SNR, might have issues with variability, interference, noise, you name it. But this is where digital can come in, and where we can basically use digital observation from the signals to basically fine-tune and adapt our front-end circuits to become more accurate. So some lessons that basically seem to permeate, and I believe you see a lot more of this adaptivity happening and self-healing happening in our chips of the future. So to kind of wrap it all up, some final musings, things that basically that I've been kind of playing around with is it's maybe time for a new Moore's law. Remember, energy minimization is what we basically call for, and trying to get as close as possible to KTLM2 might be the right thing. So nature and evolution has found in the biological human brain a pseudo-optimal solution that basically balances the size, power budget, cell complexity and size from the different cells, how small should the neurons be, and wiring density. So that's kind of, it's amazing that nature in itself has converged to this point. And I don't claim that it's finished. Actually, this is evolution in motion, and you'll see maybe brains will change over the years to come. But the question is now, given our knowledge about the physics, the materials, the nano devices, the noise and energy constraints, can't we derive what such an optical solution would look like for a physical computer? Will it basically be similar, or will it be fundamentally different than what we've seen in the biological world? And this may be too simplistic, though, because ultimately we realize there's some fundamental difference between the biological computing, the chemical computing, as electrochemical computing, and the purely electrical computing. Because there's some great disconnect that we should be aware of, and that might lead to very different solutions. If you look at the brain frequency and the computer frequency, the operational frequencies that you look at, there's about a ratio of about 10 to the 6th. As I showed you, wiring in biological is a lot slower, computing neurons are a lot slower than transistors, and so on and so forth. So there's about a factor million ratio between the two. And there's a good explanation for this, because the brain ultimately is primarily built to interact with the world around us. And the world around us is not extremely fast. We only build digital computers that fast because of the fact that we want to maximize performance. We're not built to optimize energy consumption. So if you look at this and we see that computers might come to an optimal solution, then we obviously would expect that computers will outpace brain and nature. But I believe actually this is not really going to happen. This is kind of my observation, is that ultimately what we see is this symbiosis, this convergence happening, where electronics starts happening, the electronic device I carry on me will start to interact with our biological selves. Brain-machine interfaces, wearable devices and things like that connect the humans to the digital world or to other humans through basically wireless communication and cloud communication. And potentially this is also the way we're going to be interacting with the non-biological counterparts that are rising, robotics, self-driving cars, and so on and so forth. So actually the biological and physical computer are getting more and more intertwined. And you see this in many, many different domains, right? Drones, robot, the humans interaction, prosthetic devices, and so on and so forth. So I think you really will see this convergence between various types of computing, and the interaction between the two, making that effective is really important. Finally, to wrap up this talk, one irony. It turns out that slowly but surely, we started in the electronic world, we started with basically instruction set computing, right? Instruction set computing, we program a machine. And then, but nowadays, more and more, we basically gone away from that, and we start thinking about learning-based computing as a primary basically concept. But if you back to nature, actually, if you look at the core of how our biological systems work, they're nothing else than instruction set computers, with DNA being our instruction memory and RNA basically instruction fetching, execution, and basically creating proteins that are basically the data we operate on, and that create the next set of actions. So that's the final irony. Actually, in the end, our brain is really nothing else than a instruction set computer in one way at the lowest level. And with that, I would like to conclude my presentation. Thank you for your attention. I will be happy to basically answer any questions you may have.
So thank you very much, Jan. Wonderful talk. So if you have any questions to Jan, please write the question in the YouTube chat. So we have already some few questions. So the first one by Professor Altamiro Suzin from the Federal University of Rio Grande do Sul at Porto Alegre. So there are many parallel processes running in the brain, distributed on several processing zones and interacting with autonomous systems not communicate in a constant way. The question is how all these processes cooperate on a stable and coordinated manner. Is there a supervisor?
Right, that's a good question. It's a really good question. Obviously, there is no such thing as a supervisor in the brain, and it is a distributed system. But obviously, there's a set of regulating mechanisms, things that are higher level that basically help to coordinate activities. There's actually, it's kind of interesting to see that if you look at certain parts of the brain, they actually get information from virtually every other part of the brain. They basically observe what is going on in the various regions, both actuation as well as basically sensing. And as a result of that, they basically help to set the hyperparameters, if you want to call it that way, of the system. But there's not such a thing as a single supervisor there that basically coordinates all the activities. It is indeed very distributed decision-making with some guidance of particular higher levels of abstraction in the brain.
Okay, thank you very much. Another question by Alzemiro Henrique. The inspiration in human brain seems to be driving advancements in digital processing. So can't we bugs, well, for example, as an inspiration as well, since they have a basic intelligence and use less power?
Again, a good question. And the answer is absolutely yes. The way people have, and neuroscientists have learned about how the neural system works is start from very simple critters. Things that have just a couple of neurons as an example, how they interact. And then basically, as I showed you, C. elegans is another example. People have been looking a lot at flies, various fruit flies as an example of a brain with a reasonable complexity. But again, if you look at the next levels of cognition, you go to basically primates and human primates, basically, you see that there's extra steps that have been added. But yes, the understanding we have from the simple systems in bugs and flies and things like that helps us to understand the basic concepts. But then you start layering more and more layers on top of that, that ultimately lead to the cognitive behavior that we have today. So you have to combine the various things together. You cannot just look at flies only to understand how, for instance, a human brain works.
Okay, thank you. So now a question by Marcelo Ruaro. Since our brain is most generalist and not accurate, what would be the limitations in learn from brain design to make circuits for computational problems that requires higher levels of accuracy?
Right. Again, that's a good question. And you will see, obviously, there's limitations to what the brain can do. If you really care about numerical accuracy, you want to do gigantic modeling problems or something like that, very often then a digital representation, as I said, is probably the right thing. Floating point computation is what you will need. So it might be the better solution. So there's certain problems that physical computers can do a lot better on than brains can. Brains are not very good at doing very complex type of equation analysis, for instance, or optimization as an example. However, there are other problems where you actually can say, okay, the concept of the brain is really to use, if it wants to get accuracy, it uses redundancy. It uses large numbers, it uses statistical behavior. So to me, if you look at a lot of the modeling problems we're trying to go after are statistical anyhow. So for those actually, biological computational principles might work actually very well. So if you, for instance, want to model the structure of particular very complex molecules and what the optimal optimization points are. Today, we do this with very complex digital models, but maybe physical computing, basically inspired by some of those analog equivalents that I talked about, might actually give you a similar solution with far less energy, far more efficient. So I think actually the idea of statistical computing basically where we use random set as a feature and we use the fact that we have many, many, many devices, can help us to basically build a probably better solution than what we can do today in the digital world.
Thank you. So a question by Bruce Hertz from MIT and IEEE Boston CASS chapter. So thank you, Professor Rabaey. What would you see as the most exciting application of these methods?
Mm-hmm. That's a very good question. I think the biggest application I see is definitely in the space of what, in the general term, of called robotics, right? The space where you have entities that are pseudo autonomous, that kind of make decisions on their own, learn from the environment, basically have a variety of sensing inputs, and so almost like human equivalents. That's to me the primary one, because their energy efficiency is the most important issues that are at hand. Ultimately, we want to make sure that we have a device that is robust, reliable, and can operate for a long period of time on minimal energy source. But at the same time, I think some interesting problems in physics and biology, for instance, could be solved using computational concepts like this as well. So I think we haven't really figured out what all the application domains are. There's some ones that are obvious, as I said, anything which are drones, robots, autonomous swarms, all those type of things are the more obvious ones, but I think you will see non-obvious ones as well.
Thank you very much. So now a question by Professor José Rodrigo Azambuja. So his question is, well, first, great talk. Consider the human brain is the current most advanced evolution. Can you guess what is the next evolution step?
It's a very good question. Actually, you start realizing that our brain is continuously evolving, right? Definitely over the last 30, 40 years, with the advent of more intelligent compute devices and things like that, with the internet, we have been changing the way we basically process information. things that used to be very important, that you basically had a lot of storage of information inside your brain, that's gone away. So I believe that the brain will naturally evolve as a result of that, with basically shifting functionality between different regions, augmenting certain regions, and potentially playing down some other regions. Again, it's an evolution concept, and I actually believe that we're somewhat in an acceleration today, again, because of the very fast type of impact of things indeed like learning-based device, internet, World Wide Web, all those type of things are impacting the way we basically process information. So where it's going to lead, we don't know, right? If you could predict that, would be wonderful. Maybe, but to be honest, I would be very hard for me to make a guess of where we're going to be going with. Are we going to get bigger brains? Are we going to get smarter brains? Are we going to get smaller brains? Maybe that might be an option, right? If it turns out that we can offload a bunch of the functionality of our brain to computers, maybe the brain can shrink again and become more energy efficient.
Thank you. Now we have a question by Tobias Gemek from Germany. You indicated that customization is a key principle also in nature. How does this match up with the highly flexible human cortex when compared to customized dedicated neurons as in insects?
Right. So yeah, people, I think there's somewhat of a misconception that people believe that our brain is a uniform computing platform of neurons and connected neurons. And it's like saying every chip basically has transistors and wires, right? The way those neurons are connected and basically form a certain entity is not as programmable as you think. It basically, it is very customized. Actually, you look at the various pieces of the cortex themselves, you will see customization and interconnect, the amount of interconnect and so on and so forth that exist, how they are interconnected and so on and so forth, and how the various regions are interconnected with each other. So it's not something I can reprogram easily. Within a certain region, you can, for sure. For instance, a very good example, it turns out that somebody has a stroke. A stroke basically destroys a bunch of neurons in a certain region. People actually manage to move some functionality to other neurons and be able to start speaking again or moving their hands again or something like that. But that's in a limited region. You're not going to take speech and start superimposing it on something which has to do with, for instance, vision or something like that. It doesn't work that way, unless you basically go to the very high layers of abstraction. So the brain itself is customized and is basically has been evolving in such a way that indeed various functions are implemented at the minimum energy cost. And that's definitely even more true when you go to the peripheral neural system, where we see a lot of customization happening again, depending upon the type of function you want to perform. But yes, overall, it's built on a generic platform of neurons that interconnect with each other and they basically communicate through spikes. That's true. But again, the layers above that are very dedicated to particular functionality.
Thank you. So a question by Anand Kumar Darji from India. If there are a creator of computer, do you believe that there is a creator of human brain, biological computer?
Right. So there has been no creator of a computer to start with, right? The computers have evolved. Basically, people like the good old mechanical computing first, and people like Boole that came up with digital logic, and it's an evolution, right? The computer has evolved from concepts to bigger, and it's still in the evolution. Same thing with human brain. As I said, it started 3 billion years ago with the first type of microbes and things like that started actually using some electrical activity to actuate some functionality, make some muscle move, make some motor function happening. And step by step, these things have been complicated, have become more abstract, and so on and so forth. So it's a process of 3 billion years to where we are today. Computers have evolved a lot faster, and I think we're still somewhat in infancy, and we'll still see a lot of evolution happening in computers as well.
Okay, so now I talk a question by Roberto Panepucci from CTI Campinas. It seems wildlife have evolved to optimize functions that are quite specific. What can we learn from these different brain substructures, and can we identify design strategies?
That's a very good question. Obviously, indeed, various species have been developing and been optimizing certain function based on the thing that basically makes them survive, right? Ultimately, it's again, the concept is survival. And you look at, for instance, just the difference between us humans and a dog. A dog lives by, we use vision is our primary way of interacting and basically observing the world. Dogs, it is smell. So as a result of that, if you look at the olfactory system of a dog, we have a couple of million sensors in our nose. They have at least 100 times more, a lot more sensors. And actually, they're a lot better because of the fact that they have much more redundancy. They're a lot better in smell at all. They can basically take things apart we don't even realize they are. So again, why that's true? Well, because that's the way they evolved in nature. To survive, they felt basically they have to smell what was happening, what the signs are around them, were there any predators around them, and so on and so forth. And that's true for any animal you look at. And it also explains, for instance, how certain things that were important in the early days of humanity now have changed because our lifestyle has changed. We went from hunter-gatherers to basically agricultural. And as a result of that, you've seen that our brain has evolved as a result of that. So there's many examples in nature to see how actually specific neural systems were built to do specific function. And again, is that customization task. If your goal really is, let's say, to build a robot that can live in dark and wet circumstances, you will have a different set of sensing capabilities and processing capabilities than what you have with basically something that flies or basically lives in a lot of light conditions.
Thank you very much. So now we have a question by Abe Elfadel from United Arab Emirates. So great talk, Ian. How much computing is the brain doing on the edge? Would you say that most of the C. elegans brain is on the edge?
Mm-hmm. Yes, well, the C. elegans is definitely an edge device. If you look at the neurons, it's a very simple system. It's all about motion. How does it move forward? It has some smell sensors. Some smell sensors that basically figure out where they might find something. So there's some sensors that can find food, and the rest is basically just making the motor function happen, making that worm move forward or backward. So to me, it is completely on the edge. It doesn't reason about things. It is purely action-reaction capability. Now, if you think about our brain, and you may ask, how much is on the edge? Now, again, you have to define what you mean by the edge. If the edge is basically your peripheral neural system, something that connects directly to your sensory devices, then I think actually the majority actually turns out to be more in the central nervous system, basically the brain itself is where the majority of the neurons are. Now, a lot of those are still related to edge computation, right? If you look at our cortex, primarily it's taken by things like a visual system, auditory system, some other senses, and then basically motor control. Motor control is a big function, make us speak, move our muscles so that pronounce ourselves. So if I would look at how many neurons are dedicated to higher level of abstractions, actually it's relatively small. The biggest part of our brain is really about interpreting and sensing information and performing action. That's where most of the neurons are basically going. But again, they're not at the edge, they're basically in the central computer.
Thank you very much. So now a question by Alex Hanneman from Loughborough University in UK. So with regard to what you said about redundancy, is the redundancy typically a direct replication, or would each calculation be done in different ways?
A very good question. typically the type of redundancy that you observe, the most simple one is simple replication, right? You just have too many sensors and they all have statistical variation, but ultimately the law of number works. But actually there is a number of ways where we actually use diversity to basically, if you think about a lot of the sensors, some of the things that we basically use, let's say emotion, for instance. Emotion is a direct result of actually observing a number of different parameters simultaneously. So there's diversity in the sensing and then fusion that basically helps us to create emotion. Same thing is true with stress. Stress basically translates in a number of things. Right? So it's measured in a number of different ways, but ultimately combines together into a single entity. So you have both. But the most obvious one is clearly the physical replication of the same sensor, and you basically have by using, again, at the basis of even how a neuron operates, basically it uses many more synapses than it needs to, because the SNR of every synapse is very small. So that's already the first example of a redundancy mechanism, where you basically deal with SNR by having large number of devices.
Thank you. So now a question by Professor Jürgen Becker from Karlsruhe Institute of Technology, Germany. What are the major parameters to monitor, control, verify, and qualify such models?
Mm-hmm. Now, that's a tough question. I'm trying to think about how to answer it. It's not. So do you mean models that are basically built on top of the neural system? What are the type of parameters you should observe? Again, this systems, again, designing systems like that is non-trivial. Right? We don't have a lot of experience in it. Right? These are systems that basically you cannot say, okay, here you start from bottom level, you verify that every device works, and then you basically build abstraction and you verify at every level that your functionality is correct and your performance is correct, and so on and so forth. Here we're dealing with adaptive systems which are statistical, and frankly, nobody really knows yet how to reliably build statistical systems. People have been talking about statistical computing for quite a while, and the reason you don't see them in the real world is the fact that we don't really know how to build those things effectively, how to optimize them, and how to verify and test them. So that's, to me, somewhat of a challenge that's out there. And that people are starting to think about it, but it's obviously an important challenge to think about how to do that, how to model, analyze, verify, and test basically statistical systems of this nature, which also have inherent feedback loops that do self-adaptation and self-healing.
Thank you. I have a question from Julio Torres Telo. Besides hardware, how should the software development adapt to this new paradigm?
Well, I think in a sense, software is already going that way, right? If you think about how we develop software these days for at least some of those learning systems, it's not anymore that you start basically writing tons of code. Really, what you start to say, you create a particular model, and then you excite it with lots of data and benchmark sets and so on and so forth, meaningful type of evolution scenarios and the evaluation scenarios is the way we start designing software these days. It's the software, in a sense, is not anymore in the code itself, but basically in the parameters of the code that's being generated. It's your different weights and things like that of your neural net. These are the type of, again, I believe that software has gone already to some big changes. Now, again, are we going to basically, is everything going to be driven that way? No. I think there's plenty of room left for sequential computing and sequential control and things like that. That will still happen, and instruction-based thing will still happen. But you already start seeing an evolution in the software world as well, where we create programs by basically exposing it to lots of data. The whole data science world is basically built around that.
Thank you. So now I have a question of Jorge Saez Noval. So the question is, what about the parallel sequential processing paradigm in brain-based systems?
Mm-hmm. So Again, a good question. The brain itself, as mentioned, is basically parallel by nature, right? There is no such thing as, let's say, there's no such thing as time multiplexing, for instance. We're not going to be able to, we're not basically using the same neurons to form the first time part of a task, the second time part of a task, the third part. We don't do that. So no time multiplexing. In principle, everything is concurrent. We may overlay some function on top of a single neuron. It turns out that you actually can take a neural net, a biological neural net, the brain, and train it for a particular task, and then train the second task using that same set of neurons, and you actually can map multiple functions somewhat overlaying with each other. That works, but I haven't seen any sequential. The only sequential parts are happening is because of event-driven. A particular set of neurons fires, a particular pattern occurs. The neurons fire by analogy, right? They don't have to be exact. As long as you have the right type of, suddenly you get enough energy to basically make things fire. Result of that, you fire a second region of the brain, and then the next one, and the next one, and the next one. If you look at the movie that was somewhere hidden in some of my slides today, where you saw the activity in the brain, this was actually a specific experiment that's shown. It was actually a true recording of a brain where somebody actually hears a word and has to basically respond to that word with a verb. I say ball, you have to come up with a verb that basically relates to ball and say like throw, right? So as a result of this requires basically a bunch of functions, right? You have to basically hear it first, you have to basically take it apart, and you have to recognize it. Based on the recognizing, you have to go to some cognitive thinking, relationship thinking, and ultimately you have to go to premotor and motor function where you finally say the word. It basically move your lips and things like that. That was the sequence of things, and you start seeing various regions of the brain fire up in sequence. One thing basically, the first one finishes, it basically gets enough signals into the next one fires, the next one fires, the next one fires. So the sequential behavior is really a spatial sequential. It is happening in different areas of space, not really on the same piece of hardware.
Thank you. So a question by Professor Manfred Glasner from Darmstadt University in Germany. So how much is your research technology driven, either by the advances in nanoelectronics and those in biology? And how would you get students with know-how in both fields?
Okay. Hi, Manfred. It's been a while since we last talked. Yeah, so that's an interesting question. How do you do that from research? Well, actually, my group is kind of a mixture. Obviously, we're trying to build electronic systems. And so we look very much at the evolution in electronics. And to me, one of the biggest things there is going to be 3D integration that allows us indeed to build completely different structures that were very hard to build in the past, where memory, logic, interconnect are all intertwined with each other. But at the same time, most of my students take classes in computational neuroscience. We have a very close collaboration, and they basically start learning about some of those computational models and so on. I don't claim they are pure biologists, by no means, but they basically start understanding some of the concepts that people are exploring in the neuroscience space, for instance. So yeah, having that mixture of students and having group meetings where people interact and discuss this type of things is very useful.
Thank you very much. So I have a final question for you. So as you can see nowadays, we have a lot of system on chips like the Apple microprocessors like A13, now MI, and so on, that more and more are using more and more hardware accelerators. So this may be approaching a little bit of how brain works, and can we expect to have in the future an architecture based mainly in hardware accelerators with a small CPU just to control the communication between them?
Yeah. That won't happen quickly. Obviously, if you see the majority of the realization if you look at the Apple M processor or A processors, the core of it is still very traditional general purpose computing. Obviously, with a lot more parallelism. We have many cores, we have GPUs with many trail. It's only for the peripheral function where you need a lot of computational capability for a specific task. That's where you put accelerators. And the same thing is happening in our data centers as well. If I look at the data centers and how they evolve, we see accelerators become an important part. But still, you will have an interesting balance between the more generic instruction-based computers and the specific accelerators for specific functions. So it's going to be a hybrid. And we're definitely going that way. If you look at how Facebook and Amazon and Google are building the data centers, they are becoming application-specific data centers. These are not data centers anymore for every purpose, but there's data centers for YouTube, there's data centers for this function, there's data centers for search. They all have their own functionality dedicated and optimized with the right accelerators added to the backbone, which is GPUs and CPUs.
Okay, so thank you very much, Jan.
You're welcome.
Excellent talk, very inspiring. There is a huge set here of comments congratulating you for the fantastic talk. So I will not going to read all them to you because it will take a lot of time. So thank you very much. Thank you also very much for all the audience to attend this last talk of the season of CASS Rio Grande do Sul talks this year. We had today audience from several countries, from France, Germany, Belgium, Italy, Singapore, Poland, Chile, Mexico, Colombia, Uruguay, Canada, Austria, Switzerland, USA, Taiwan, India, United Arab Emirates, and for sure, Brazil also. Probably there is from some other countries that we were ashamed to include their name in the chat. But anyway, it's an impressive number of attendees from many locations in the world. So this is one of the good results of the COVID, that now we can reach remotely people from many locations. And we are able to have this great talk of Jan being transmitted, broadcasted to globally. So thank you very much again. And I also would like to ask you all to sign to this YouTube channel if you want to be informed about the next events. I just would like to remind you that next week we have the CERESA, the International School on Effects of Radiation Embedded System for Space Application. So it's free registration for all our IEEE CASS members. You can go to the website to see the full program. And also the week after, the Seasonal School in Electronic Design Automation, also free registration to all IEEE CASS members. So you can go to the website to see the full program. And then I also would like here to give the word to José Rodrigo Azambuja to close this as chapter chair of our chapter Rio Grande do Sul, to do the closing remarks for this season of CASS Talks.
So thank you, Ricardo. Just some very quick words here. I would like to thank you again, Jan Rabaey, for closing our season. This is officially our season 8, but this is the first season that actually goes live on YouTube. So some numbers. This is our 52nd talk in this year. So this means one talk around every week. And if we consider the events such as the South Microelectronics School, the CASS workshop, the DPV-SA, which happened in the end of October, we would have many more talks. So I would like to thank specifically Ricardo for being our program chair. He has been in every single talk this year. So this is a huge amount of work, a huge amount of time spent for the CASS community, for IEEE. And also thank Rafael Luis and Jean for doing the editing and thumbnails and uploading to YouTube. This is another huge amount of work that we do specifically for our members and for the ones who subscribe to our channel and to whoever actually wants to watch our talks. So thank you so much for participating this year. Next year we should start in February, so we should have the season 9 of our CASS talks next year, and stay tuned for updates on when we actually start them. So thank you again, Ricardo, and thanks for all our audience for watching our videos. I hope you like it. This is why we do everything that we do. This is why we invite our speakers. This is why our speakers are here. I'm sure this is probably why Rabaey is also here to give this great talk to our audience. So thanks to you all. Thank you, Ricardo.
Thank you all. Have a nice weekend.
Bye now.
Bye-bye.
Nice evening. Bye-bye.